For question 14.09, we're given the value of Kp for the following reaction. We've got two molecules of nitrosyl chloride decomposed to nitrogen monoxide and chlorine gas. And the Kp for that is 0.018. And we're asked to find the Kc of that reaction at equilibrium at 300 degrees Kelvin. And so sometimes Kp and Kc are identical, right? Kc is concentration, and Kp is based on partial pressure. So it just depends on what we're given. If we're given ATM, that's a partial pressure. If we're given molarity, we're calculating Kc based on concentration. The equation to convert between those two is Kp equals Kc RT delta N, where R is the universal gas constant, 0.0821 liters ATM mole Kelvin from chapter 10. T is absolute temperature, so we're looking for temperature in Kelvin. And delta N is our change in moles during the course of the reaction. And we're going to determine that by moles of products minus moles of the reactants. So when there is no change in moles, when the change in moles from the starting material to the product is 0, Kp equals Kc. Because if we were to raise RT to the power of 0, that becomes 1, and it would fall out of our calculation. So I'll just repeat that, When there is no change in moles, if I had a reaction with 2 moles of gas on the left and 2 moles of gas on the right, delta N would be 0. And so when I raise R times temperature to the power of 0, it becomes 1, and then 1 times Kc would equal Kp. So if there's no change in moles, Kp equals Kc. We do not have that in this case because we have 2 moles of nitrosyl chloride gas at equilibrium with 2 moles of nitrogen monoxide gas and 1 mole of chlorine gas. So the first thing we should do is find what is our change in moles. So we want to find out moles of products minus the moles of reactants. So I have 3 moles of products and I have 2 moles of reactants. So my delta N, my change in moles, is 1. Now I can find out what is the equilibrium constant based on concentration for this reaction. So I've got Kp equals Kc RT delta N. I'm going to divide both sides. I want to get Kc by itself because that's what I'm looking for. So I'm going to divide both sides by RT delta N. And so that cancels out here, and I'm left with Kc equals Kp all over RT delta N. Now I can plug into my calculation to determine Kc. Kc equals, well, my value of Kp, 0.018, over my value of R, 0.0821 liter ATM mole Kelvin, times my absolute temperature. They did us a favor. They already gave us temperature as Kelvin. And all of this is raised to the value of 1. So if I multiply and divide, and yes, you might be wondering right now at this point in time, there's a lot of units associated with R. There's mole, there's liters, there's atmospheres. Only the Kelvin would cancel out. Equilibrium constants are unitless, so there are no units in this final answer. I just included the units that are associated with the conversion factor. So I do that calculation and I get value of Kc equals approximately 7.3 times 10 to the minus 4, or 7.3 e to the negative 4. So again, if there's a change in moles during the course of a gas phase reaction, then Kp and Kc would not be equal to each other. If moles were identical on the left and the right, then Kp would equal Kc. So in this case, we do have to do a small conversion